All right, yeah, I'm on. Awesome. Hello, everyone. I'm CCP Relativistic, and I'm going to tell you about black holes. Not the black holes that you see in our video games, but rather the black holes you can not see in our sky. Yep, clicker works. Like I said, I'm CCP Relativistic. I'm a senior software engineer working at CCP Games on eFrontier. I have a PhD in computational astrophysics. Actually, Carolina, my notes aren't visible. So, yeah, I'll keep on going. I know this slide at least. I've been at CCP for just over 2 years. And like I said, I have my PhD in computational astrophysics from the Aveiro University in Portugal, where I researched what's called hairy black holes with scalar and Procca hair. I won't talk about that today, really, because it would take some hours to do, probably. But basically today, I'm going to tell you about black holes. What they are, mainly. We're going to look at like the first ideas behind black holes. When did physicists and scientists start thinking about black holes, and what were like the first ideas behind them? Next, we're going to think a little bit about how do we describe them, both with words and equations and physics and everything, all the tools we have at our disposal. And then we're going to look at whether they do actually exist, because that was not, we didn't really know until somewhat recently, and you could still argue that maybe we don't still know, maybe we just have a really good idea that they might exist, but you know, we'll see once we get there. That was a funny slide. There we go. Okay. I love this comic. It's from XKCD, if you know it. It's how to fold the real origami black hole. There's the first step where you fold the paper once. Then there's the second step, and then you just keep going 190 times, and that's enough to fold a piece of paper into a black hole. At that point, you've put all the mass inside its own source-field radius, which means that it should technically collapse into a black hole. I don't have a piece of paper, so we can't try. But we'll like you can do it at home, maybe at the hotel or something, as long as it's not close to me. Okay. The clicker is being weird. Okay, so we'll start with the first ideas. And the first ideas for black holes were something called dark stars. And it was basically this thought that what happens, I'm just going to keep going through the quote. What happens if you think about a star that is so dense that its escape velocity is faster than the speed of light? And John Mitchell, back in 1783, so really early when we knew a bunch about stars and we knew that other points in the sky were other stars, but they were thinking along these lines of like, what happens if gravity is so strong that not even light can escape it? And they calculated it, and interestingly enough, they actually get to the same conclusion that we do today regarding the size of the black hole, but for the complete wrong reasons. So the equation is exactly the same thing, like the diameter or the radius of the object that they found is the same as like Einstein and Schwarzschild and all the other physicists found in last century, but like I said, for the completely wrong reasons. Laplace also found this independently a few years later. This usually happens in math and physics. People are like, well, doesn't anymore because we have the internet. But back then, it used to because people were kind of researching along the same avenues, but they might have not only met like once in their whole life. So they didn't really know what each other were doing. So they often came up with the same things. Like calculus was invented by two different people, one in England and one in Germany. But this suggested that light was actually influenced by gravity, and they made that assumption. But a few years later, physicists decided that actually light isn't affected by gravity, which was the wrong assumption, by the way. Physicists are sometimes wrong, which is fine. So they thought it wasn't influenced by gravity at all, so they basically stopped thinking about this. Like, dark stars can't exist because light isn't affected by gravity. Do some other research. A few hundred years later, they started thinking about it again. This is the first definition of a black hole, like a modern black hole. And as you can see, it just says black holes are areas of space-time from which nothing can escape. And I'm being very particular with the choice of words here. I'm not using points of space, volumes of space. I'm using areas, because space-time, which I use here, which I'm not really going to define in more detail than space-time is really just space. 1, 2, 3 dimensions, back and forwards, up and down, left and right, plus time. So it's when you combine them all. it's much more complicated than that. It would take a full course at university level, math and physics, to actually understand what it means. But for now, just think about it, 1 dimension of time, 3 dimensions of space. And that's space-time combined into one. And that's really all it is. And notice that it doesn't actually say what I said earlier, this thing about, oh, you would need to move faster than light to be able to escape. I say nothing can escape. So even if you could travel faster than light, you still couldn't escape this definition, right? It's not like, oh, it has to be larger than c to be able to escape. And that is actually true. Nothing can escape a black hole because just like all roads lead to Rome, once you're inside the event horizon of a black hole, all roads, literally all of your future paths, no matter what you do, lead to the center of the black hole. There is no way out of it, regardless of what you actually try to do, which is a fun thing. Next one, mathematical definition. Now, like, you think you're about to see an equation, but we're actually going into set theory, which is like, at least for me, first grade Iceland was the first thing I learned in math. It's like, oh, I have apples and oranges. Draw a circle around the set that you can make. And that's what we're about to do, but for black holes. So, a black hole is the complement of the chronological past of future null infinity. In equation, this. Right. We can skip over the explanation, right? Because this is very obvious. No. Okay. Good. I heard there was like one person that said no, so we're actually going to go through it. That's fine. Future null infinity is really just fancy math and physics speak of where light ends up if it travels forever into the future. So it doesn't hit anything, it doesn't get absorbed by anything, it doesn't reflect of anything, it just goes into the future forever. Which kind of sounds like everything, right? If there's light coming from all places and it ends up there at infinity, okay, great. Perfect, right? Okay. Chronological past of future null infinity. So the chronological past of something are all the points which could have emitted light which reached infinity. So for example, I'm standing not on Earth, not on the moon, but somewhere in space, so not standing, floating, and I shoot a laser. If that light just travels on forever until infinity, then the chronological path, then that point at which I was at is a part of the chronological past of future null infinity. Why does it say null? That's usually the question. Like, what's this null here? The thing is in space-time, things travel along something called geodesics, which are basically the shortest paths between 2 points in curved space. Actually in all space, but namely in curved space. And light travels along long vectors that have length 0. If you don't understand that, that's fine. It's not important, but I just wanted to say it. Then, complement of. That just means everything that is not in the other thing. So if you think about the point that I was standing at, and I shoot light out, and that light reaches infinity, then I know that that point is in the chronological past of future null infinity. So the complement of that is everything where light doesn't reach infinity, which is really, if we go back, really just this thing, right? I just spent like 5 minutes explaining this thing here in this really complicated way. Why? Because it's more rigorous. We can actually do math with this stuff. Not math that I'm going to do today, no, don't worry. But like this is one of the formal definitions. Like if you read a book called The Geometry of Space and Time by Stephen Hawking and George Ellis, this is actually their first definition. They don't define it by the other sets of equations that I'm about to show you on the next slide. So, and I call that one the physics definition, because that's actually the one where we can do calculations and predict things, not just prove weird facts about black holes, but actually calculate things, like how big they are and stuff like that. Black holes are solutions to Einstein's equations for a particular set of conditions. I'll tell you what those particular set of conditions are for some examples later, but for now, just think about it that way. These equations are this thing here. Sometimes this factor here is written as GAB, but these things here are something called tensors. This is the Ricci tensor and the Ricci scalar. This is the cosmological constant and the metric tensor and the stress energy tensor. Completely clear. Basically, what this equation says is space is curved, And matter, the stuff that is in space, tells it how to curve. But then the curvature of space also tells matter how to move. So it's like a back and forth thing of like space-time is curved. You have this thing of like there's a sheet and heavy things curve it. But then that stuff moves along the curves. For example, we have the Schwarzschild solution, which was actually found the year after Einstein published his theory of general relativity, which was in 1915. The year later, 1916, Karl Schwarzschild, I think it was a German meteorologist, and get this, in the trenches of World War I. He was on the front lines, in the trenches. He somehow got a hold of Einstein's paper on general relativity. He's like, oh yeah, great. There's one solution here that I can find. Obviously named after him because of that. And that's the solution. Doesn't really tell you much, right? Like, how does this solve this equation? Well, these terms here actually describe this GAB thing, and this R and everything is a part of that. His solution describes a spherically symmetric vacuum solution. Everyone got that? Yeah, okay. Spherically symmetric just means that the solution behaves the same around the ball on this side and this side, as long as it's the same distance away from it. So it doesn't depend on the angle that you're around it. As long as you're the same distance away from it, like the radius, it's the same solution. And you see it from that. There's no dependence on any angle here. There's just the m, which is the mass of the black hole. There's the r, which is the radius away from it. And there's nothing else. There's a 1, there's a 2, there's something called dt, dr, d omega. These are measurements along, so dt just measures how far you're moving in time, and dr measures how far you're moving in space. So thinking about 1 dimension in time, 3 in space, that kind of just tells you that. And what you see immediately is that, like just if we look at the behavior of these equations, if r is really, really big, like millions of meters or whatever unit you prefer measuring distance in, and m is just a constant, it doesn't change, then this thing here is basically 0, which means that this is just 1, this is just 1, and you get what we call flat space. There's just like time is measured with a negative sign, and space is measured with a positive sign, but there's no scaling of anything. But you see that if it is not, if like r is close to 2m, but still larger than it, you basically see that the measuring time gets really funky the closer you get to the black hole. So the surface of the black hole, called the event horizon, which I'll tell you about in a minute, is at r equals 2m when this thing here becomes 0. So from this perspective of this equation, you basically can't measure time because time doesn't change. Basically, a worse thing happens here, because what happens to this equation if r is equal to 2m? You get 1 minus 1, which is 1 divided by 0. Error. You can't. So we say that like this form of it really tells you it shows you that there's a special surface at r equal to 2m, beyond which you kind of things start making less sense. Let's put it that way. Because just to be really quick here, if r is now smaller than 2m, this number here is larger than 1. What does that mean for this thing here in the parentheses? It means that 1 minus something that is larger than 1 is a negative number, negative, negative, you get a plus, which means that time is now not negative anymore. It's basically changed sign in terms of interpretation of it as a coordinate. That's all I'm going to say about the insides of a black hole, but it's an immediate sign that like something is wrong. Like we can't really describe it, which is fine. There are plenty of books that do try to describe it, but I'm not going to. All the previous definitions assume that there is a surface which separates the black hole from the rest of the universe. The surface is called the event horizon, like I just told you. It happens for the Schwarzschild solution at r equals to 2m, but for different solutions, which I'll tell you about later, it happens at other radii. And sometimes it's not even a sphere. If we break the assumption that we have a spherically symmetric black hole, it might be a squished sphere or something even crazier. Interestingly enough, this event horizon, or the surface, isn't actually that interesting. In the coordinates that we used earlier, which are just the regular Schwarzschild coordinates, it is obviously very bad, because if you go to the surface, the equations kind of break down. But there do exist coordinates where it's a completely fine surface. And even astrophysically speaking, of like speaking about traveling into a black hole or something like that, if the black hole is heavy enough, you could actually go past the event horizon and you would not be vaporized or pulled into spaghetti strings or whatever. Because that's basically what happens for normal sized black holes, like stellar black holes, which are like roughly 2 times or 3 times as heavy as our sun. If you pass the event horizon, the gradient of the tidal forces there is so high that your toes are being pulled faster into the black hole than your head, which rips you apart into little strands of spaghetti. For large black holes, such as the black holes that are at the center of our galaxy and stuff, that doesn't happen because this effect, this like tidal forces, they're not that strong for big black holes. Which sounds counterintuitive, but if you do the math, which I encourage you to do, it actually works out. All right. And like I said, for isolated black holes, remember when I said spherically symmetric vacuum solution? I forgot to mention that. Vacuum just means there's nothing around it. There's no mass other than the black hole there. And for those, there's actually nothing special at the horizon. If you are, however, an observer outside watching someone fall in, there is something very special. You will probably see them being vaporized and stuff, but there are a bunch of interesting phenomena that happen when stuff falls into black holes, whether you are the person falling into the black hole or you're outside watching. We're not actually going to go too much into that. I'm going to discuss other things today. Okay, this sounds weird, right? No hair theorem. Why would I be talking about no hair? Took a second, right? Took a second for everyone to get it. And mathematically speaking, black holes are actually very simple objects. And that's not like a gag. I'm not joking or anything. And what I mean by that is that when we describe things mathematically, we can define something we call degrees of freedom for that particular system. And just to understand it, imagine, I'm not going to do it, but imagine I'm going to throw the remote into the hall. Okay, how many numbers do I need to define? Let's say we're all experts on Newtonian mechanics. How many numbers do I need to define such that I know where it lands? I'm not asking for the answer, I'll tell you, don't worry. So, I'm going to throw it. I need to know, and you'll just have to believe me, you can ask ChatGPT after the lecture. Initial velocity, angle of throw, like am I throwing it parallel to the ground? Am I throwing it at a 45-degree angle? And like I said, initial velocity, how fast do I throw it? And technically, the elevation difference of where I threw it and where it lands. So this is actually a bad example because this is slanted, but you could still do it if you would probably need a fourth. But so you see, we need 3 numbers, maybe fourth for the slant of the not the benches, I guess. So we need those 3 numbers or 4, which as like initial conditions for the equations we use to completely solve the system. We know everything about it. We know the full trajectory of the remote as it travels, and we know where it lands. We even know how fast it lands. Like we know the momentum of it as it smashes into whoever is unlucky enough to get it in their face. So it's a system that has, let's call it 4 degrees of freedom. How many degrees of freedom do you think the Schwarzschild black hole has? Let's go back. How many? There's really only 1, right? There's the mass. Okay, so which system is more complicated, mathematically speaking? A black hole or me throwing the remote into the crowd? Technically throwing the remote, right? Because I needed 3 numbers. As long as we know the math and understand the math. It's actually a bad example because I don't think anyone would agree that the number of degrees of freedom would determine how complicated something is. But it is an interesting thing because it somehow tells you how simple the system is in terms of just describing it. Okay, where am I? There I am. Okay. So basically, in classical general relativity, once we let the black hole rotate and have electric charge, we can describe them by their mass, electric charge, and angular momentum, and that's it. And at the end, I'll show you a really nice quote which summarizes this. But for now, that's all you need to know. You can fully describe black holes by these 3 parameters. What does that mean? Okay, that means that if the black hole has a temperature, as Stephen Hawking predicted, you can calculate that temperature from these 3 parameters. That is different compared to a star, because if we have our star that has a mass, angular momentum, and probably some electric charge. If you then take another star somewhere else in the universe that has the exact same mass and the same angular momentum and the same electric charge, they probably have different temperatures. So there's other degrees of freedom for which hair is a metaphor that describe it. Black holes, therefore, have no hair. It was John Archibald Wheeler, a physicist back in the, I think, 60s or 70s, that basically coined this term, and Jacob Bekenstein alongside him. All right. Yeah, they have no hair. So we basically have these black hole solutions. We have one, there's the Schwarzschild that I showed you. Then there's something called the Reiser-Nordström solution, which has mass and charge. There's a Kerr solution, which is mass and angular momentum. And then Kerr-Newman, which is mass, electric charge, and angular momentum. I'm not going to promise that this was the most math that we're going to do, but this was the math-heavy part. OK, so black holes that matter, as in the black holes that are up there. Not black holes on a piece of paper or in the computer, which we solve mathematically, but the stuff that is out there. So we believe that astrophysical black holes shed their electric charge. So basically, most black holes that we see in the sky have no electric charge and are thus just described by the Kerr metric, which was discovered by Roy Kerr, a New Zealand mathematician. Discovered them in the 60s. So you see that was about, 50 years after the initial Schwarzschild solution. It took a while. It is no joke to actually do it. I did joke that all the other math earlier was actually somewhat easy to do. This is not. I don't know many people who could actually do this. It's insane that he did this at that time. And for them, and this will come in handy later, due to the rotation, they actually pull space-time along with them in a certain region that is called the ergo region or the ergosphere, where basically, just like inside the black hole, you have no choice but to go towards the center. But if you're in this ergosphere, you have no choice but to rotate with it. And this creates really interesting behaviors in like accretion disks. And there's a lot of sci-fi which uses this to extract energy from the black hole and stuff like that. And the phenomena that I was just describing is called frame dragging. OK, that's all great. So we know that there's stuff in the sky. We know there's mathematics that describe this. But actually, like, what are they? I haven't really said it. Like, there's nothing. I haven't said like what is the mass at the center? Where did it come from? So the first kind of observations of black holes, or the first evidence that we actually, because as you can see, the math happened over 100 years ago. Einstein actually said, like, no, this doesn't make any sense. There would be no way that anything could be this dense. Well, maybe 30 years ago, we started observing the center of our own galaxy. And we saw that there are stars that orbit something close to the center. And if we do our Keplerian mechanics, we actually see that the thing there is heavier than anything we've ever seen before. About 4 million times heavier than our own sun. But the orbits of the stars that came close to it are way, way, way too close to be a star. Like, if this was a star of 4 million times heavy as our sun, the stars that orbit it would actually go into its surface. So that doesn't make any sense. So we basically know that the density of Sagittarius A star is higher than any known form of matter, because we know that, if you compress electrons down into a really small ball, you get a white dwarf, and we know the density of that. If you do the same to neutrons, you get a neutron star, and this was heavier than both. And we actually know the size of neutron stars and white dwarfs. So basically, people said, OK, the only mathematical explanation for the thing that is there, that is so heavy and so dense, is a black hole. We've never calculated anything that could actually explain this other than a black hole. So I ask, is that proof? Have we seen a black hole at this point? Not really, right? We've seen that things orbit something that is very small and very dense. And sure, our current understanding of physics at that time, 30 years ago, says that there isn't anything else that could be this dense. But that might just mean that our physics isn't good enough yet. There might be things that, like other forms of matter, where you condense quarks into a star or something. Maybe, who knows? I love these videos. I'm going to show you 2 videos which actually show this. So you see that, like, in the center, there are some fuzzy stars that are obviously orbiting something. This is like the artistic view of the video. The next one is the science one, where we actually have markers and names for all the stars. We have the date up in the right left-hand corner, and then whatever the center of the thing that they're orbiting is there. And you see that they move around, and they orbit it weirdly. And again, if you had the data, you did the calculations, you did your Keplerian mechanics, you would see that, wait, they're passing way too close for this to be a star or any form of matter that we know. So that was kind of one of the first evidence of black holes that we knew, observationally speaking. There was some other ones, like quasars and stuff earlier, but I don't think they actually thought those were black holes until we figured it out after this stuff. So we're now going to move on to black hole formation. Like, where do they come from? I'm not going to say this is cheating, but I will mention in the last point of this slide why. So basically, at the end of their lives, sufficiently massive stars explode in a supernova. Off the top of my head, I don't remember a movie which shows a supernova, but you have probably all heard about supernovas. I think even one happened in Eve at some point. If the final mass of the remnant that is left behind, because what happens in a supernova is there's like core collapse. So it basically runs out of fuel, it starts collapsing in on itself, but then it explodes out and throws a bunch of matter out, and then there's like a core of stuff left in the center that is then being bombarded by the stuff that is escaping and going back in and blah, blah, blah. Very violent process. If that remnant is heavy enough, and today we know it's about 2.2 to 2.9 solar masses, you'll actually see that these are all the names you know from Oppenheimer, the movie, because this is one of the first things he was famous for. We know that it becomes a black hole if the remnant mass is that heavy after the supernova. If it's not heavy enough, it becomes either a neutron star or a white dwarf. There are different limits for that. There's the Chandrasekhar limit for, I think, white dwarfs, and then a different limit for neutron stars, which the name escapes me right now. And stellar black holes, as in the black holes that are in solar systems, like they're the result of stars in solar systems blowing up and leaving behind a black hole. They're formed this way, but there are other types of black holes, supermassive black holes, and we honestly don't have a good idea of how they are formed. And I was going to talk about this, but then I looked at the program of Fanfest, and I saw that Dr. Becky is presenting tomorrow about how supermassive black holes grow. Because the problem is that if you take the maximum amount of stuff supermassive black holes can eat, and you multiply that by the age of the universe, we still have black holes that are heavier than that. So there are black holes that are so heavy that they shouldn't be able to exist. And I'm not going to answer that. She will hopefully do it tomorrow. So I encourage you to go to that talk tomorrow. I managed to skip a slide, basically. OK, so really quick, just black hole classification. Usually, when I did my PhD, there were only 4 classes of black holes, but I guess they added a 5th one. But basically, we have micro black holes, which are like of the mass of the moon. They're very small, not even 1 millimeter. So if one passed through here, you probably wouldn't even see it. We have never obviously observed them. There was a worry a few years ago at the Large Hadron Collider that one might be formed when they would smash stuff together there, but they said it wouldn't happen, so we did it anyway. Maybe we'll see them one day. I honestly doubt it, but never say never, right? Stellar black holes, the ones that I told you about, they range from a couple of solar masses up to 150, maybe a bit more. The radius scales like this. So you see that a 2 solar mass black hole will have a 6-kilometer radius, and up to 450 solar masses. And then we have the intermediate mass black holes. We hadn't actually observed those only like 10, 12 years ago, because those are not existent in solar systems, and they're not at the centers of galaxies. So there was this remaining question of like, oh, shit, where are they? But we have seen their gravitational waves at this point, and we'll discuss gravitational waves in a minute. So that's an interesting thing, that they are not from solar systems, but they're also not at the center of galaxies, but we have observed them from gravitational wave observations. Then there's the supermassive black holes, and honestly, ultramassive black holes should just be within this here, but I guess we needed something to separate 1 million to 1 billion solar mass heavy one and 1 billion to 100 billion solar mass black hole, because that's very important. They're huge. Even supermassive black holes become larger than our own solar system. Ultramassive black holes become larger than 10 times our solar system, 100 times our solar system. So they can become absolutely huge. And I think this is at the limit of what we've observed out there. So how do we see them? We've already discussed the orbit thing. So, stars orbit something really heavy, really dense, but that's not the only way to see them. We can actually observe gravitational waves from merging black holes, and just by directly looking at them, right? If you've heard about the Event Horizon Telescope, that's actually what they did. So starting with gravitational waves, the stellar black holes, they form binaries at the center of a solar system. There's two of them moving around each other. Slowly, over time, that orbit gets closer and closer because it's emitting energy through gravitational waves, by the way, but we've never measured those. We only measured the merger. And we know from general relativity, and actually a subsection of general relativity called numerical relativity, which uses computers to calculate this stuff, that they should produce gravitational waves. And we could talk about this for like the whole day, basically. But the gist of how they measured it is really just like a simple, I'm not going to call it a Michelson-Morley experiment, if any of you have done a university level like physics course. But it's basically, you have a laser that shoots a beam through a beam splitter, through some test mass. It gets reflected. This one goes here and there. And if the beams, or the tunnels, in fact, that the laser beam was sent through are equally long, they should meet here at the same time. However, when a gravitational wave passes through stuff, it actually like squeezes and pulls things apart, really, like in a really little way. And then if you observe then you observe that in like one beam arriving a tiny bit earlier or later than the other one, and from that you can calculate the amplitude of the gravitational wave and everything. This is an insane technical marvel because what they had to do, the length of the tunnels here was 4 kilometers, and the deviation in length of the laser beam was 10 to the minus 18th meters. Yeah, so 0.17 zeros, 1 meter. So that is smaller than all our atoms and like all of that stuff. So it's insane that they could measure this, but they did. And here's the waveform. Here are actually 2 waveforms because they built 2 of these on the east and west coast of the United States. And we see that they basically measured the same signal coming through where they shifted and inverted one of them. But how do we know that these were actually black holes? Again, I haven't, like nothing about what I said in these points here really tells you that it's a black hole other than that you have to believe me. Numerical relativity lets us simulate these things, like I told you. And what they did is they created, or they ran the simulation of smashing things together, like 2 black holes, 2 neutron stars, 1 neutron star, 1 black hole, and calculated the signal that the Earth should see. And they did this probably for thousands of different cases of like, well, one small black hole, 1 big black hole, 1 small neutron star, 1 big black hole, and so on. Big distances, at an angle, all of that. And then they just see that one of their simulations actually fit with what they observed. The way that I like to explain this is, imagine if I told you all to go outside down to the harbor. I would go out on a boat, a kilometer away. Amazingly enough, the water is completely still in Iceland. Never happens, by the way. No one laughed. You don't live in Iceland, obviously. The ocean is never still in Iceland. But anyway, let's assume it is. I stand at the edge of the boat. I drop a pebble in. The waves travel to you guys, and you measure the waves. Could you, theoretically speaking, tell me the size, shape, and weight of that pebble? And the answer is yes. We probably, like not any of us in here, but someone probably could with enough numerics and calculation power. That's basically the same thing. The 2 black holes smash together, waves travel through space-time, a bunch of light years to us. We see that. We simulated what would have happened, and sure, it agreed. We're agreed. So I'll ask the same question as before. Is that really observing a black hole? Sure, obviously, yes, but it's still like you could ask the question, maybe not. So then we get to the Event Horizon Telescope. And that's the question of like, can you see it? And the answer is no. There's nothing emitted from the black hole, but we can see its effect on the things that emit light around it. So astrophysical black holes have an accretion disk, which is just a disk of matter which orbits the rotating black hole. And basically what happens is, well, no, let's go one back. We'll start with how do we see. I promise I'm not speaking to my 7-year-old daughter or 9-year-old daughter when I'm explaining this, but this is kind of how I explain it to her. The way that I see you guys and you see me is that the light up there goes from the bulb or whatever is emitting the light. It goes to my head or my shirt. Let's take the shirt, for example. It hits it, reflects, lands in your eye, and your eye interprets that as the color of my shirt, which is black in this case, which is not a great example. But for everything else, it's ray tracing, as you've heard about in video games, right? But so how do we do in video games then? We do the reverse, right? So I imagine that my eye is a camera, and it shoots a bunch of photons out for every single pixel that you want to see. And you basically do the physics simulation of like, oh, it bounced off the wall, and then it went there, and it came from there. Oh, so it's blue. OK, and then you do that for millions of pixels, and you get an image. You do the same thing for a black hole, right? You start as an observer here. I'm doing this in a plane, not in full 3D right now, because it's much easier to explain this way. You shoot a bunch of rays out, and you ask, which ones ended up on the black hole? Draw them black. Which ones did not? Draw them red. And you see some sort of image. You keep doing this for all of your whatever, all the latitudes of your field of view, and you get an image of it. So basically what you see is not the black hole itself, but you see the lack of something, which is like the distorted image of the event horizon due to gravitational lensing and rotation. Anyone seen this image? This was actually done, like this thing here, I did this in like 2013 on my laptop in Portugal during my PhD. This thing here was done in 1979 on an IBM 7040 computer by Jean-Pierre Luminet in France, and is hand-drawn. So he had punch cards, probably written in Fortran, that he plugged into a thing, and he calculated the path of light and the gravitational lensing and the intensity of the light, which I didn't do earlier, right? I was just calculating paths. He actually calculated how bright they should be based on an accretion disk. And then he stood on a blackboard and doink, doink, doink. And that's the image. Absolutely insane. Today, we have computers that do it for us. On the left, we have the actual observed images from the radio telescopes that looked at M87, which is the central black hole of one of our neighbor galaxies. In the center, we have a simulation of the accretion disk around a black hole using something called general relativistic magnetohydrodynamics. This is a much different picture than this one here, because this one has amazing resolution. What we're looking at here is a really, really blurred version of whatever we see at the black hole. So if you apply the same kind of blurring to these pictures here, you basically get the same thing. So which part is the black hole? It's obviously not this one. You're just seeing the accretion disk and the lensing. It's the central part. It is the lensed part of the event horizon. It's the place where no light came from. Again, just like with everything else, we could talk about this the whole day. You could read papers about it. You could read articles. This was all done a few years ago, many years ago, actually. But honestly, my favorite part about it is there's a Netflix documentary about it. I think it's just called Black Holes, and then some subtitle. It is honestly very good, and it's nice because you actually get to see the scientists who did this. My favorite fact about the whole project, weirdly enough, is that the data that they gathered to draw these images was so large that it took less time to ship it in a ship or an airplane than send it over the internet. It was 1 petabyte of data that they had to move between all the different observatories in the world. And you get this really small fucking picture, right? Like, yeah. Okay. This is also a nice way of explaining it. You basically have a camera plate that is looking at a black hole, and this is why you usually see an image like this due to gravitational lensing, you're seeing the back of the disk being like lensed above it, and the front end is just the same, but then you also see the lower half of the back of the disk being gravitationally lensed behind and reaching you. This image changes depending on how you're viewing it. Like if the black hole is in front of me, if I am viewing it from above, it looks like this. If I view it edge on, it's completely different. From below, completely different. So this is nice to think about, but it's still not like what you would always see when you look at a black hole. But this one was really popular when Interstellar came out, because this is what was used usually to describe those. All right. I'm actually going to skip these so we have time for questions. If you want to know about whether black holes have hair, you can ask me afterwards. But for now, we're just going to end on this quote, which I really like. I'm just going to read it. In my entire scientific life, the most shattering experience has been the realization that an exact solution of general relativity discovered by the New Zealand mathematician Roy Kerr provides the absolutely exact representation of untold numbers of massive black holes that populate the universe. Was Chandrasekhar, an Indian physicist. I did actually end my PhD thesis on or what? Because my PhD thesis was about black holes with hair, which actually violate this stuff here, but I'm not going to talk about that today. I'm done. Thank you so much for coming, and we have time for questions. The one up there.
You said a couple of times that nothing escapes the black hole. Can you say how that relates to Hawking radiation, please?
No. Yeah. So Hawking radiation is one of those things where early on, after it was discovered, people came up with an analogy that is honestly wrong. So if any of you have read about Hawking radiation, the analogy is that in the vacuum of space, or in the vacuum of everything, pairs of particles are constantly forming out of the vacuum energy of empty space. So you will get like an electron-positron pair that forms up, and then they meet each other and annihilate. So technically nothing happened. You created a particle and an antiparticle, then they met, and they evaporated. And then people thought, wait, Hawking just came up with this radiation thing. Maybe we can explain that by this phenomena, that a particle pair formed really close to the horizon of a black hole. And the one with negative energy, the one that we don't really want to see, fell in, and the other one escaped. And we see that as radiation. That's like the typical analogy of Hawking radiation. It is wrong. That is not what happens, sadly. And the worst, and it's going to get worse, by the way, the only way to understand it fully is just to study quantum field theory and curved space, which is one of the most difficult physical theories you can ever study. So honestly, there's not a great answer to it. But at least from that math, because we've not observed that at all, because the Hawking radiation, the temperature of it is actually lower than the cosmic microwave background for most black holes, which means that technically black holes should be feeding from the cosmic microwave background and growing from that rather than evaporating. But let's assume that we have black holes that are in completely empty space with no cosmic microwave background. They would, at least according to the math that Hawking did, emit radiation, which means lose mass, which means slowly shrink, and eventually something. No one knows. Which is honestly the answer. There's thousands of papers and ideas of what might actually happen there. There's something called the firewall theory, which I'm not even going to try and explain. But there's a bunch of things. If you've heard of string theory, loop quantum gravity, unification of gravity and quantum forces, that is one of the main problems they want to solve. What happens when you have insanely strong gravity, but you're also at such small scales that quantum effects happen? So honestly, no answer, but still an answer of like, yeah, mathematically speaking, we think that they should shrink if they would be in the right environment, but they're usually not. Hopefully that's at least somewhat of an answer. Okay?
What do you think about the idea of our universe being inside the black
perfect. It's an amazing, like, I'm not going to say everyone who studies this thinks about it, but the equations look so similar that it's a very intuitive thought to have. Like there's the metric that I showed you for the Schwarzschild solution is what describes a black hole. And then when we're describing the whole universe, cosmology speaking, we use something called the Friedmann-Robertson-Walker equations, which are equations that are just like the ones that I showed you, the Schwarzschild one. They're just different terms. And that they depend on time. You know, it's not a static solution like the Schwarzschild one is. But for certain values, they look exactly the same. So people obviously thought, like, wait, that actually could make sense, that like we live inside a black hole. The event horizon of the black hole is the cosmological horizon for an expanding universe. And it is, like, yeah, there's a reason why people think that happens, but it's not. It's hard to explain, but mainly about the thing that, like, all roads lead to the center. There's no center of our universe as far as we know. So that's basically the first one, that like, okay, inside a black hole, you literally cannot travel in a direction without moving towards the center. And there is this joke that even if you try, you're just going to go faster to the center, which is like partly right. If you have a spaceship and you try to leave, you're just actually accelerating faster to the center for certain scenarios, but not all. So that's the main one. Because as far as we know, there's not a center to our universe. We're just in a really insignificant place. Like, our universe is homogeneous and like, well, there's no preferred direction in it. It's just like completely, I'm not going to say empty, but it's, yeah, at large enough scales, it's homogeneous and isotropic, basically. So, yeah. All right.
So thanks for the nice presentation. And so my question is, so you're working 2 years now for CCP, and so we get black holes in EVE Online who destroy everything, or we can't escape?
It's a really easy answer. Like I said at the beginning, I don't work on EVE Online, so like you're all good. I work on EVE Frontier. So that's the political answer. But obviously, we can, you know, games do whatever they want, right? If you've seen Interstellar, they actually go into the black hole. Maybe there's a library there, maybe there isn't. Probably not. So you know, in a video game, we could do whatever we want. But just to answer you a bit better, though, in the game industry, there are so many fields that we touch upon that we have actually done black hole stuff. Like I'm a software engineer. I work on the gameplay side of Frontier. So I'm coding the game systems that are being put into that game. But at one point, our creative director comes to me and asks, like, hey, do we know what 3 black holes look like? I'm like, no, I don't think so. Why? Oh, we want to do some trippy gravitational lensing artwork for the game. I'm like, okay, let me look into it. And it turns out that you can like do the ray tracing that I showed you earlier for 3 black holes. And so some of the key art for Frontier actually came from those physics simulations. And just to advertise myself maybe, on Saturday, 11 a.m. in Silverberg, I'll actually be talking about how we used astrophysics to generate the world of Frontier. So. Yep.
Okay. Could you use the lensing effect of black holes to observe an event twice that happens on the other side?
Not just twice, an infinite amount of times.
An infinite amount of
yeah,
times.
because it's really interesting if we just go back, and I played around with this a lot in my PhD when I wrote the code that did this thing. By fine-tuning the angle that you shoot the photon at, you can almost completely control where the photon ends up. So if we have a look, you see that this red one here, it actually will escape because I drew it red, right? I did the simulation. I know that it's going to escape. So it is actually going to wrap around it. I think it's just behind the black one, so we don't see it, and it might be taking a long time to do it. There is, and just to go even further, there is a surface outside of the event horizon of a black hole called it's usually called the light ring or the light sphere, which if you stand at and if you look along that surface, you will see the back of your head. Because at that exact surface, light can actually orbit the black hole. So just like, our planet, the Earth, orbits the sun, the moon orbits the Earth, you can actually have light orbit black holes. So it can have circular orbits around it, which means that if you stand in that orbit and look along it, you will see the light that left. I mean, you would have to have like a headlight on the back of your head, obviously, but yeah.
But wouldn't it then be that you're seeing your past
Yes.
ahead
Yeah.
in
Yeah. Depending on the orbital period, basically. Yeah.
We have the last question.
If your head's not spaghettified. So I told it was last question, so I have two questions.
Okay.
Have you collaborated at all with Kip Thorne over at Caltech?
No,
No?
but I sat behind him once. That's as close as I could get.
So since I'm the Space Pope, I'm a member of the Athenaeum of Caltech. And next time in Los Angeles, give me a call. I'd love to host you
Awesome.
at Caltech.
Will do.
So,